Hi everyone, let's work out an NMR problem. First thing I like to do is take a look at the chemical formula and calculate degrees of unsaturation. What you want to do is calculate how many hydrogens a saturated compound should have and subtract the actual number of hydrogens, making some modifications for any heteroatoms like halides and oxygen, nitrogen, and then divide by 2. This is going to give you the number of pi bonds and or rings. Okay, for this compound, there are 5 carbon atoms. So the number of hydrogens, if a 5-carbon compound was saturated, would be 2 times 5 plus 2 more. The actual number is 12. And then what you want to do is make some modifications for heteroatoms. And what I remember is +1, 0, -1. And for every halide, you add a hydrogen. For oxygen, you don't make any change. So O and O, that's kind of nice. And then if you have nitrogen, then you subtract 1. Okay, what about sulfur here? Sulfur is in the same column as oxygen. So it belongs to the same family, same group, and we're going to assume that sulfur is going to behave like oxygen here. So let's ignore it, just like what we would do for oxygen. So ignore the sulfur atom and let 12 be the actual number. So 2 times 5 is 10 plus 2 more is 12. Subtract 12, that's 0. So the compound is saturated. Cool. No pi bonds, no rings. Okay, so now it's time to look at the NMR spectrum. And you can start a couple different places, but what you need to consider are the number of peaks. There are 3 here. Let's label them A, B, and C. And the number of peaks tells you the number of types of hydrogen. So we have 3 different types. The position, well, you can go to the correlation table and get some ideas. Now be careful with the correlation table. The correlation table gives you averages or typical values. And there can be lots of variation in real molecules. But it's a good place to start. So we have peaks around 1, 1.3, and 1.6. So maybe methyl or secondary or tertiary halides. Allylic, well, that's not possible here because that's a degree of unsaturation. There's a pi bond. Now, sulfur is not on this table, but again, we're going to consider it to be like oxygen. So here's oxygen, here's oxygen. Oh, I missed this one. Oxygen's over here, but there's a pi bond, so that's out. And here's some pi bonds to these oxygens. Okay, so maybe the sulfur could be a thiol group or a sulfide group. And maybe the chemical shifts might be in this vicinity. However, oxygen is more electronegative than the sulfur, and it's electronegativity that's shifting the peaks downfield, so maybe they're not going to shift. The sulfur atom may not shift the hydrogen as far downfield as 2.5 to 5 or 3.3 to 4.5. We're going to have to be a little lenient. Okay, so as a preliminary guess, I'm going to say maybe these are alkanes. Actually, all 3. They might be all 3 are alkanes. But there's that sulfur atom in the chemical formula. So maybe a thiol or a sulfide. And I'm leaning towards the last one for that. Just based on position, thinking the sulfur atom might be the most electronegative and shifting it downfield. Okay, that's my guess. Remember, correlation table, don't trust it overly. But it's a nice start. What is more trustworthy, however, are 2 more things. The integration, or area of the peaks, and splitting. So I like to look at the peak intensity, the relative areas, and as a quick check, just make sure that the areas add up to the total number of hydrogens. There's 12 over here, and this doesn't add up. 1 plus 2 plus 1 is 4. We only have 4 H's if we were to accept these areas at face value. And the computer that generated the spectrum doesn't know what the chemical formula is. All it can calculate are the areas underneath the curve, and that just gives you ratios. So the ratio is 1 for peak A and 2 for peak B and 1 more for C. That just says that there's twice as many hydrogens producing peak B as A or C. But now if you use the chemical formula, you see that there's a total of 12. Well, all 12 hydrogens have to show up in your spectrum. You need this to add up to 12. And the only way to do that is to multiply all these values by 3. So peak A is not 1 hydrogen, it's 3 hydrogens. Peak B is not 2, it's 2 times 3, or 6. 6 hydrogens are producing peak B, and peak C is, again, 1 times 3, 3 H's. There we go. So 3 plus 6 plus 3 more is 12. That counts for all our hydrogens in the molecule. That's integration, or peak areas. Now let's take a look at splitting. It's a little hard to see, but if you stare at this a while, you can see that there's a little bump there, 2 up here, and 1 more right there. We got a quartet. And what you do is you take away 1 from the number of peaks you see. So I see 4 peaks there, 4 split peaks. You take away 1, you get 3. We have 3 neighbors. These 3 hydrogens have 3 neighbors. Okay, if we look at peak B, it's a singlet. Take away 1 from the number of peaks. 1 minus 1 is 0. This has no neighbors. And then finally peak C. I see 1, 2, 3 little bumps. That's a triplet. And take away 1 gives you 2 neighbors. Okay, now that we identified the number of hydrogens in each peak, the integration values, and their neighbors, now you want to try and match them up. And let's see, let's start here. There's these 3 neighbors. Where are they? Well, can't be up here in these 6 hydrogens. They have no neighbors. So these the hydrogens from A can't be neighbors to them. They have to be neighbors to C. Okay, the same thing should be true over here. Peak C, these 3 hydrogens, say they have 2 neighbors. Uh-oh. We don't have any peaks that only have 2 in it. So that's a problem. Now, they can't be neighbors with themselves. So you have to rule out C. C can't be neighbors with C. That makes no sense. B, well, I'm trusting the splitting. It's a singlet. There are no neighbors. So that leaves A. Okay, that is weird. Peak C, which is produced by 3 hydrogens, have 2 neighbors. Okay, they must be contained in peak A. So only 2 of the hydrogens or A are really neighbors to C, leaving 1 hydrogen that's not a neighbor. I know, that's weird. But that's how I interpret this spectrum. Okay, let's see. Let's see how we can put this together a little bit. Make some guesses as to structure. Let's go back over to C. C says that they are 3 hydrogens that have 2 neighbors. So let's put that together. Peak C is 3 hydrogens, and they say they have 2 neighbors that come from A. There's still 1 more hydrogen we have to take care of. There's 1 hydrogen that's not a neighbor. Let's save that somewhere else. Another carbon must have that extra hydrogen in it. Let's take care of B. B has no neighbors, but there's 6 hydrogens. Well, to make 6 hydrogens, we need 2 methyl groups. And they can't have any neighbors. They're shifting down the same position. They are all equivalent. So we have to put a little mirror plane here so that this methyl group sees the same chemical shift as this methyl group. And then this carbon that the 2 methyls are attached to, they can't have any H's. Okay, and that's peak B. Peak B. The chemical formula is C5H12S. So I've used up all my carbons. Let's take this carbon right here, attach those 2 methyl groups. Those are peak B. Can't have any H's on this side or that side. Well, that's okay. We'll put a that's an ethyl group. Let's put an ethyl group on one side. And this methyl group at the end was peak C. This carbon with 2 hydrogens is peak A. And what do we have left over? I used up all 5 of my carbons, C5. 12 H's, well, I got 3 plus 2 is 5. 3 more is 8. 3 more is 11. I'm missing one. Oh, yeah, because I thought, well, maybe it belongs to another carbon. But if I put an H here, that's going to break this trend. It's going to give neighbors to those carbons. Oh, what about sulfur? Sulfur, like oxygen, prefers 2 bonds. So let's connect the sulfur here. And that gives sulfur 1 bond. The only atom left is another hydrogen. So hey, I didn't use this one little feature here. We were told an SH proton absorbs near 1.6. 1.6 is that problem peak, that A that says it integrates to 3 hydrogens, but the splitting of peak C says there's only 2 neighbors there. Okay, so what's happening is we have overlapping peaks. So just by coincidence, darn it, this hydrogen attached to sulfur has been shifted downfield to the same position as these 2 hydrogens. And so they look like they're equivalent, but they're not. Okay, we leave anything else? We've labeled our peaks. The hydrogens that produce each of the peaks are correctly labeled. We have all the atoms in our chemical formula. I think we're done. Cool. Let's try another one. Here's the chemical formula, C9H11BRO. So the degrees is going to be 2 times 9 plus 2 more, minus the actual number of hydrogens. There's 11, but we do have bromine, so add one more. Oxygen, ignore, divide by 2. So we have 4 degrees, which means we could have 4 rings, we could have 4 pi bonds, but the most common way to take care of 4 or more degrees of unsaturation is perhaps 3 pi bonds and 1 ring, the benzene ring. There's a ring, and then 3 pi bonds. Okay, so anytime I see 4 degrees or more, I think benzene ring, and then immediately jump to the correlation table. The benzene ring shows up twice. Here's the benzene here. So hydrogens directly attached to the ring are downfield around 7. If there are any methyl groups or any ethyl or any carbons directly attached to the benzene ring, we call those benzylic hydrogens. They're going to show up around 2.5. Okay, right here we have some peaks around 7. That's highly suggesting we do have a benzene ring. And we also have some peaks down here around 2.5. Maybe those are the benzylic hydrogens. What about that halide? Well, halides show up in a broad range between 2.5 and 4. So these down here could be the bromine attached to a carbon, and it's a hydrogen, right? That's producing one of those peaks right next door to a halide, the bromine. We also have an oxygen. Now, there were 4 degrees of unsaturation, and all 4 were taken up by the benzene ring. So this oxygen cannot be a carbonyl. That would take up another pi bond, and we don't have 5 degrees unsaturation. So only look at functional groups that have a single bond to oxygen. That's the alcohol and the ether again. And so those are between 2.5 and 5, and 3.3 to 4.5 typically. That's in the same range here, ether or an alcohol. Okay, so the correlation table is giving us some suggestions. Let's look at integration next. Adding them up, we get 5.5, but the total number is 11, and so we're off by a factor of 2. And the peak at 2.3, this one right here, really is 2 hydrogens, 3.58, 2 hydrogens, 4.08, 2 hydrogens. This one at 6.9 is 3 hydrogens, 1.5 times 2. And then we have this peak here, 2 hydrogens. And I'm going to go ahead and label these A through E. Okay, let's look at the splitting. Down here in the benzene region, we see 1, 2, 3. So this peak looks like, well, it is a triplet, which means it has 2 neighbors. This one, 1, 2, 3, 4. That's weird. What are the other peaks? Usually it's symmetrical, right? Look at this nice symmetrical peak over here. The little one's on the outside, big one in the middle. That's not the case here. And so if something's splitting oddly, you probably have overlapping peaks. And I think that's what's happening here. We do have 4 peaks, so it kind of suggests a triplet, but we're not sure. I'm not sure. What I do know is that it integrates a 5, and all of these hydrogens should be on the benzene ring. There's a 1 bond to the benzene ring that allows us to stick on the other atoms in the chemical formula, and then there's 5 hydrogens on the ring. And now we can go after the triplet. This hydrogen can't be neighbors, or it's unlikely to be neighbors with the group over here, let's just put a carbon hydrogen, because that would be 1, 2, 3, 4 bonds away. And splitting's typically 3 bonds away. So this hydrogen has 1 neighbor, so we're expecting a doublet. This hydrogen has 2 neighbors. That could be our triplet. This hydrogen, 1 neighbor up there, 1 other neighbor down there, could also be a triplet, and this one too, 1 neighbor on either side. But this one's going to be a doublet. So the doublet here can't be peak A, so it must be peak B. Same is true for this one. And in fact, there's a symmetry plane right here. So B, this top B is equivalent to that bottom B. Where's peak A? Well, this one does have a triplet, but it's a single hydrogen. How are we going to get 2 H's to be equivalent? Well, let them be on opposite sides of this mirror plane. So I think this one is A, and this one is A, which means this one is B. Yeah, that kind of explains how they're overlapping. Let's look at peak C now. Looks like there's a little bump there, 1 more up there and up there. So C is a triplet. Take away 1, you get 2 neighbors. This peak is produced by 2 hydrogens. Peak D, well, I see a little bump there, 1 up high, another one there. Same situation. Triplet, 2 neighbors, 2 hydrogens produce it. And then peak E, well, we got the expanded view here. Although, I don't know if we need it. I see 1 peak there, another one there, 4th one there, and a little 5th one here. And if you blow it up, it's nice to see all 5. We have a, what is that called, a quintet. But anytime you're over 4 peaks, you can call a multiplet. And that's because sometimes there's a tiny little peak off the sideline, off the side of these peaks, that may be just too small to see. Might be just lost in the baseline. So just allow for a little freedom that there's at least 4 neighbors here, but there could be more. And there's 2 hydrogens. Okay, the chemical formula is C9H11BRO. Let's see what we can make of this. We took care of the benzene ring. There's 6 carbons in the benzene ring, and we put 5 hydrogens there. Got 2 hydrogens here, here, and there. That's 6. That takes care of all 11 hydrogens. But where's that bromine? Where's that oxygen? Oxygen's more electronegative than bromine, so maybe that's C, attached to a carbon with 2 H's. And now this carbon is making 3 bonds as I've drawn it, so there's still a 4th bond. D, well, maybe that's the hydrogen connected to bromine. Maybe. So put a bromine here. Put 2 carbons. Sorry, 2 hydrogens attached to a carbon. And so I've taken care of the O and the bromine. Taking care of 2 more carbons. That's 8 altogether. 6 on the ring, and these 2 carbons is 8. I need 1 more carbon. Well, stick those 2 hydrogens on it. And now this carbon still needs to make 2 more bonds to have a total of 4. And I stare at this a little while and realize these are kind of like puzzle pieces. The benzene ring has 1 more spot to connect the rest of the groups. And so is this this group. There's just 1 more bond to connect. Same is true for this group. 1 more bond to connect. Sorry, I was missing one. It's like, how am I going to get all these together? This group has 2 bonds. Oxygen. Oxygen makes 2 bonds. There we go. Okay, so this one has 2 more bonds to make, 2 more bonds to make. This one only has 1. And this one only has 1. And so they must be at the ends of the molecule. Right? So I'm going to put a benzene ring down here. And then this other group, I'm going to put the other end. That's my peak D. And now we have to decide, do we put the CH2 group, then the oxygen? So that's the CH2 group. That's my peak E, because it's benzylic. And then I have this O, and then a CH2. And this would be C. That's one idea. Or I could have attached them the other way. Get the benzene ring here, and then put this group on next. OCH2. That's my peak C. And then this group with 2 bonds, that'd be peak E. And then the last group, the CH2 with the bromine, that'd be my D. Okay. Then let's look at the position of peaks to see if we can eliminate one of these structures. This peak E over here is the one that's farthest upfield. It's farthest from anything that's going to shift it downfield. And there's 3 functional groups that are shifting hydrogens downfield. The strongest is the benzene ring. Then there's an oxygen and a halide. Peak E is farthest from all 3 of those groups. If you look in this structure here, this E is right next to the benzene ring and right next to the oxygen. I'm expecting that peak to be downfield. That doesn't make much sense. It doesn't. This structure and this group right here doesn't make much sense relative to where the peak position is. This makes more sense. These hydrogens are farther from the oxygen, farther from the halide than any other hydrogen in the molecule as it's drawn. And then this peak that we call peak C, it's right next to the oxygen, the most electronegative atom, and then the halide is a little bit upfield, D. This structure makes the most sense. Okay, we have all our peaks labeled. Got a good structure. Thanks for watching.